I'm going to try to explain every electronic component in a single video. So let's start with a little recap of some basic components. First up, we have a resistor. The purpose of a resistor is to resist current flow, and this value is represented by that color code on the stripes. If it's a bigger number like 10 ohms or 100 ohms, then it's a low-value resistor. If it's a smaller number like 100 kiloohms or 100 ohms, then it's a high-value resistor. Also, if you have a band that's gold or silver on the end, this tells you the tolerance of that resistor. So if it's gold, then the resistance value can be off by 5%. And if it's silver, then it can be off by 10%. Now, when electricity flows through a resistor, we get something called voltage drop. This is because the resistor converts electrical energy into heat and light, which is why resistors often get hot and glow just a little bit. Now, all these things are losing power from our circuit. So what we get at the output of the resistor will be less than what we started with at the input. Next up, we have a capacitor. The purpose of a capacitor is to store electrical energy. You can think of a capacitor as a rechargeable battery, but unlike a battery, a capacitor does not have any chemical reactions taking place. It just stores electrical energy in an electric field. Basically, one side of the capacitor will become positively charged, and the other side will become negatively charged. And the amount of charge we can store on each plate is equal to the capacitance rating. This is measured in farads. Now, capacitors come in two types. There's electrolytic capacitors, and there's ceramic capacitors. Electrolytic capacitors can store a lot of charge for their size, but they tend to be more expensive and have a limited lifespan, since the electrolyte eventually leaks out. Ceramic capacitors are cheaper and last longer, but they can't store as much charge for their size. Now, when we attach a power source to a capacitor, we get a rapid rise in voltage until it reaches the same voltage as the power source. And once it reaches this point, no more charge can be stored. So after that, the capacitor acts like an open circuit. Next up, we have an inductor. An inductor stores energy in a magnetic field. To do this, we pass current through a coil of wire, and the more current we pass through the coil, the stronger the magnetic field becomes. This creates a reluctance to change in current flow. So inductors resist changes in current flow. And this is why inductors are often used in AC circuits to filter out certain frequencies. Now, inductors don't have any moving parts, so they don't make any noise when they're in use. They also don't produce any heat. So unlike resistors, they're 100% efficient. Next up, we have a diode. The purpose of a diode is to allow current to pass through it in only one direction. A typical example would be a regular Schottky diode that allows current to pass through easily in the forward direction, but blocks current in the reverse direction. When we put a diode in series with a LED, the diode will allow current to pass through in only one direction, ensuring that the LED lights up in the correct direction. Diodes also have a voltage drop across them. This means that if we measure the voltage across the diode, we'll find that it's less than the input voltage. And just like a resistor, this voltage drop is caused by the diode converting electrical energy into heat and light. Next up, we have a transistor. The purpose of a transistor is to amplify or switch electronic signals and electrical power. A BJT transistor has three terminals: the collector, the base, and the emitter. And the way we control which direction current flows is by varying the voltage on the base terminal. If we increase the voltage on the base terminal, this increases the current flowing from the collector to the emitter. And this relationship between the input voltage on the base and the output current from the collector is what we call the transistor's gain. There are also other transistors besides BJTs, like JFETs and MOSFETs. And while the internal operation of these transistors is quite different, they all serve the same purpose of amplifying or switching signals and power. Next up, we have a thyristor. A thyristor is kind of like a transistor, except it's more powerful. A normal transistor can switch and amplify small amounts of current, but a thyristor can switch and amplify much larger amounts of current. A normal transistor has 3 terminals, but a thyristor has 4 terminals. These extra terminals allow us to vary where the current starts flowing. This is useful in applications like servo drives, where we need precise control over the amount of current flowing. Next up, we have an integrated circuit. Integrated circuits are basically a bunch of transistors and other components placed very close together on a single piece of semiconductor material. One simple example would be a timer chip, like a 5x5 timer. It has 3 legs. We connect a power source between the positive and negative legs, and then we connect whatever circuit we want to control to the center leg. A 5x5 timer outputs a repeating waveform at a specific frequency. This waveform can be used to control servo motors, LEDs, relays, and countless other applications. Another type of IC would be an operational amplifier, or op-amp. An op-amp has 2 inputs and 1 output. Whatever voltage we put on the inverting input will come out on the output, but inverted. The non-inverting input is usually connected to ground, so it's not used very often. Op-amps are often used as filters or signal conditioners. Another type of IC would be a microcontroller. A microcontroller has a bunch of pins. Some of these pins can be used as digital inputs or outputs. These can be used to read signals from push buttons or turn LEDs on and off. Microcontrollers also have analog inputs, which can be used to read signals from sensors. Microcontrollers also have a clock signal, and this can be used to make the microcontroller do something over and over again at a specific interval. Microcontrollers also have program memory, where we can upload our own programs to make them do whatever we want. One popular microcontroller is the Arduino Uno. It has a wide variety of pins that can be used for digital input, output, and analog input. Another type of IC would be a microprocessor. A microprocessor is basically a more advanced version of a microcontroller. They both have similar features like digital input, output, and analog input, but microprocessors typically have more processing power and are used in more complex applications. Another type of IC would be a printed circuit board. No, seriously, printed circuit boards are actually considered to be an electronic component. And this is because a PCB is basically a non-conductive material with conductive traces embedded inside of it. By placing components on top of the PCB and connecting them to these traces, we can build entire circuits. Another type of IC would be an FPGA. An FPGA is a chip that contains a bunch of programmable logic blocks and a small microcontroller. The advantage of using an FPGA is that we can reprogram the logic blocks to do whatever we want. This makes FPGAs very useful for prototyping new designs before committing to an ASIC. Another type of IC would be an ASIC. An ASIC is basically an integrated circuit that's custom designed for a specific application. This means that an ASIC can be smaller and more efficient than an FPGA, but it also means that it's much more expensive to make. Another type of IC would be a module. Modules are basically a bunch of integrated circuits placed together on a single piece of PCB material. One common type of module would be a motor driver. Motor drivers can control servo motors, stepper motors, and DC motors. They typically have a few inputs, a power supply, and a ground, and then a few outputs that connect to the motor itself. Modules can also be used to generate specific waveforms. For example, there are modules that generate sine waves, square waves, and triangle waves. These waveforms can then be used to amplify, filter, or otherwise manipulate the signal. Modules can also be used to convert voltages. For example, there are modules that convert a lower voltage to a higher voltage, or vice versa. These are called step-up and step-down converters. Modules can also be used to display information. For example, there are modules that display numbers, letters, and other information. These are called character LCDs and graphic LCDs. And finally, we have a breadboard. A breadboard is basically a blank canvas for prototyping circuits. We can place components onto a breadboard and connect them together with wires. Breadboards are useful for testing out new circuit ideas without having to commit to making them permanent. Now, I tried to cover every electronic component that I could think of, but if I missed one, please tell me in the comments below. If you learned something in this video, hit that like button. If you want to see more videos like this, hit that subscribe button. And as always, thanks for watching.